Power transformers are static components that transfer energy from one electrical circuit to another by means of a magnetic circuit. These machines are employed to change the voltage level to decrease power losses along the cables due to high current. Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to invite you to observe the solution of 8 exercises related to power transformers that frequently appear in exams for electrical engineers. Let's go to the first. For the ideal transformer of the figure, calculate all the phasor currents and voltages. Also, find the power delivered to the inductive load. Okay, my friends, this is the exercise. Let's go to the solution. The exercise provided this information. It said that the voltage of the power supply is 1000 volts and the resistance of the cable is 10 ohms. Alright? With this data, we can calculate everything. Alright? When we are requested to consider a transformer as ideal, it means there will be no losses in the machine, okay? This is what we are going to consider. So let's go. Let's calculate all the voltages and the currents and the power delivered to the load. Firstly, to calculate the voltages and currents, we have to refer this impedance to the primary side of the transformer. This is what we are going to do. We are going to reflect this impedance to the primary side of the transformer. It is going to be ZL prime equal to N1 over N2 squared times ZL, okay? The exercise said that the turns ratio of the transformer is 10 to 1, okay? Then we use 10 to 1. Therefore, it is going to be 100 times 10 plus J20, and this gives a value of 1000 plus J 2000. Alright? This value represents this impedance but referred to the primary side of the transformer. Alright? And now what we need to do is to combine this impedance with this resistance, and we are going to call it the total impedance. The total impedance seen by the source. Okay, this is the impedance seen by the source. The total impedance, ZS, is the impedance seen by the source, which is R1 plus ZL prime. And it is going to be 10, okay? 10 plus 1000 plus J 2000. And then it is 1010 plus J 2000. Alright. With this, we can calculate the current. But before we may convert this to polar, okay, This is the Cartesian representation of the complex number. We are going to change it to polar. Because it facilitates our calculation. I prefer using the polar form in some situations. Okay, we are going to have to divide this by this to get the input current, and to do this it is preferable to use the polar form. Alright, now we can compute the primary current and the voltage. The primary current I1 is going to be the voltage of the source divided by the total impedance, or the impedance seen by the power supply or voltage source. And this is 1000 phase 0 degrees divided by 2240.5 phase 63.2 degrees ohms. Consequently, the value of the input current, or if you prefer, the value of the primary current is 0.446 phase negative 63.2 degrees amperes. Alright, this is the value of the primary current. And with the value of the primary current, we can calculate V1. V1 is this voltage here. To calculate V1, we do not use ZS. We are going to use ZL, okay? Because the resistance R1 has its own voltage drop. V1 is not here. V1 is here, okay? So V1 is equal to I1 times ZL prime. And this is equal to this, okay? 0.446 phase negative 63.2 degrees amperes times this 1000 plus J 2000. And when we multiply one by the other, we get 997.2 phase 0.23 degrees volts. Alright, we already have I1 and V1. Now we are going to compute V2 and I2. Alright. Subsequently, we use the turns ratio. We're going to need to use the turns ratio of the transformer to compute the secondary current and voltage. Okay, V2 is going to be equal to N2 over N1 times V1 times V1. Okay? And okay? And this is equal to 1/10 of V1, which is equal to 99.72 phase 0.23 degrees volts. Okay? This is the value of V2. You just divide this by 10 and you get this. Now, Similarly, we calculate I2. I2 is going to be equal to N1 over N2 times I1. And this is 10 times I1. And we find the value of 4.46 phase negative 63.2 degrees amperes. All right? We have calculated I1, V1, V2 is a tenth of V1, and I2 is 10 times I1. Okay? This is a step-down transformer, which means that the secondary voltage has to be less than the primary voltage. Okay? Observe that the secondary voltage is less than the primary voltage. But the effect causes, this effect causes the secondary current to be greater than the primary current. The secondary current is greater than the primary current by the turns ratio. The turns ratio is 10, then the secondary current is 10 times the primary current. Okay? This is what we needed to calculate related to currents and voltages. Now let's calculate the power delivered to the load. I'm going to erase it here to calculate the powers. With these values, we can calculate the power delivered to the load. Okay, the complex power delivered to the load is the output voltage times the complex conjugate of the output current. And we need to use the values, but observe here that it is not the actual output current, it is the complex conjugate of the output current. Then if we use the values that we just calculated, we're going to find 444.75 phase 63.43 degrees volt ampere. Alright, this is the complex power delivered to the load. To calculate the real power delivered to the load, we take this number, which is the apparent power. The apparent power is the magnitude of the complex power, 444.75, and multiply by the power factor. The power factor is the cosine of this angle here, 63.43 degrees, and this gives a value of approximately equal to 199 watts. This is the real power delivered to the load, and the reactive power, Q, load, is equal to 444.75 times the sine of 63.43 degrees, which is approximately equal to 398 VAR. Okay? So we have calculated everything that the exercise requested of us. It is all for exercise 1. Let's go now to exercise 2. Exercise number 2. For the circuit of the figure, calculate the percentage of the generated power lost in transmission with no transformers in the circuit and when 2 tend to 1 ideal transformers are used. Okay, my friends, this is exercise number 2. Let's go to the solution. Letter A, without transformers. Without transformers, we have this simple electrical circuit. When there are no transformers, the generated current, the line current, and the load current are the same. The current of the generator, the current along the line, and the current delivered to the load are the same. Okay? We're going to call this current I simply. And the value of I will be the division between the voltage of the power supply, 100 phasor degrees volts, divided by 10 ohms plus 10 ohms, which is 20 ohms. Therefore, the value of the current is 5 phasor degrees amperes. The power lost in transmission is the value of the resistance of the line times the magnitude of the current squared. And this is 250 watts. And now to calculate the percentage of the generated power lost in transmission, we need to calculate the generated power. The generated power is 100 volts. The magnitude of this voltage times the magnitude of this current times the cosine of the angle between them. As there is only resistive elements in the circuit, the power factor is 1. In other words, the angle is 0 degrees. Therefore, the generated power is 500 watts. Alright? With these values, we can calculate the percentage of power lost in transmission. The percentage of power lost in transmission is equal to 250 divided by 500 times 100. And this is 50%. Okay? This is what we want to measure and compare. We want to measure this parameter and compare it to the one we're going to get when we use transformers. Just to illustrate, we can calculate also the power delivered to the load, and the power delivered to the load is going to be the resistance of the load times the current delivered to the load squared, and this is 250 watts, okay? Of the generated power, only half of it is being delivered to the load. The other half is being lost in transmission, okay? This is the result that we wanted to find to assess the importance of transformers for power systems. Now we're going to do the same using two identical 10-to-1 power transformers. Let's put them in the circuit. We're going to use one power transformer here. Ten to 1. Now, firstly, 1 to 10, and the second is going to be 10 to 1. Okay? We're going to step up the voltage here and then step it down to deliver power to the load. This is the current of the generator. This is the current of the line. And this is the current of the load. Okay? And now we need to measure the importance of putting transformers in power systems. And we are going to assess whether we can greatly diminish power losses along cables when we use power transformers. Firstly, we refer the load impedance to the line region. We are going to refer this load impedance to the line region. The technique that we are going to use, we are going to refer the load impedance to the line region, combine with the line impedance and refer it to the region of the generator to calculate this current, the current of the generator, okay? R low prime is going to be 10 to 1 squared times R low, okay? It is going to be 100 times this, which is 1,000. Now, subsequently, we combine this with this, and we call it equivalent resistance, HEC. The equivalent resistance is RL plus RLow prime, and this is equal to 10 plus 1,000, 1,010 ohms. Okay? To finish, we refer this equivalent resistance to the generator side. And again, we use the turns ratio, but see that the voltage here is greater than or larger than the voltage here, and the voltage here is less than or smaller than the voltage here. Okay? Then what we're going to do is simply the equivalent resistance referred to the generator side is going to be 1 over 10 squared times the equivalent resistance, which is simply the division between this number by 100. And it is 10.1 ohms. We use this value to calculate the current of the generator. We have something of the sort. Okay, so IG is simply the division of 100 phase 0 degrees volts by this resistance here, 10.1 ohms. And this gives a value of 9.9 phase 0 degrees amperes, okay? But observe that these are identical ideal transformers, okay? Whenever speaking about ideal transformers, we do not care about the losses within the machines. Only when dealing with real transformers, we compute and account for the losses in the machines, okay? Whenever talking about ideal transformers, we neglect the losses and observe that they are identical. So IG is going to be equal to ILO, okay? We can understand that. And the IG is equal to ILO, the current delivered to the load. All right? To calculate ILE, you're going to need to use the turns ratio of the transformer. ILE is equal to 1 over 10 times IG, which is 0.99 phase 0 degrees amperes. Okay? We have calculated everything now. With these values, we can calculate the main question of this exercise. We want to assess, to evaluate the level of losses with and without transformers. With the line current, we can calculate the power loss in transmission. The power lost is equal to the resistance of the line times the current. Okay, the magnitude of the current squared. And this gives a value of approximately 9.8 watts. Okay? And we want to compare this power lost with the generated power to assess the percentage of it. Okay? PG is equal to 100 volts. Okay? The voltage of the power supply times the current of the generator, 9.9 amperes times the cosine of the angle. We are dealing only with resistive elements, then the angle is 0, and we find a power of approximately 990 watts. Okay? The power delivered to the load, we can calculate the power delivered to the load. The power delivered to the load, R low times I low squared, and it is approximately equal to 980.1 watts. All right? And the percentage of power lost in transmission is going to be the power lost in transmission divided by the power of the generator times 100%, and this is equal to only 1%. Okay? Only 1% is being lost now along the transmission line. And what is the conclusion that we get? We concluded that the power transformers are very, very important for power systems. Okay? Because in letter A, when no transformers were being used, 50%, half of the generated power was being lost in transmission. And with the use of two power transformers, we have greatly reduced from half of it to only 1%. Okay? With the employment of two 10-to-1 power transformers, we will reduce the level of losses from 50% to only 1% of the generated power. Okay? This result demonstrates how important transformers are for power systems. Okay, now let's work with real transformers. Exercise number 3, a 6,600 440 volts 50 Hertz single phase transformer has an equivalent reactance of 0.05 per unit and an equivalent resistance of 0.02 per unit. Find the full load voltage regulation at 0.8 lagging power factor if the primary voltage is 3,300 volts. Okay, my friends, this is the question. Let's go to the solution. For inductive loads, okay, for inductive loads, because it is a lagging power factor, it means inductive load. For inductive loads, the full load voltage regulation is, we are going to use this model here for inductive loads. And working with magnitudes only, we can confidently say that E2 is equal to V2 plus I2 times the equivalent resistance times the cosine of the angle plus the current times the equivalent reactance times the sine of the angle. Okay? Observe that by definition, voltage regulation is E2 minus V2 divided by V2, okay? Which is the voltage at no load minus the voltage at full load divided by the voltage at full load. Okay? from this and working on this equation here, we simply pass this to this side here, okay? We pass V2 to this side, it becomes E2 minus V2, okay? And we divide it all by V2, and we get that the voltage regulation is going to be I2 times the equivalent resistance divided by V2 times the cosine of the angle plus I2 times the equivalent reactance divided by the voltage times the sine of the angle, okay? If you understand how we moved from here to here, you have everything to understand what's going to come next. Observe that since ZB is equal to V2 over I2, which is the base impedance, okay? We are going to use this as the base impedance, then I2 divided by V2 is equal to 1 over ZB. Alright? We're going to use this here to get to the expression we're going to use. The voltage regulation is going to therefore be the equivalent resistance divided by the base impedance times the cosine of the angle plus the equivalent reactance divided by the base impedance times the sine of the angle. Okay? This divided by this the actual value of the equivalent resistance divided by the base impedance is the equivalent resistance in per unit, and the actual value of the equivalent reactance divided by the base impedance is the equivalent reactance in per unit. Alright? With this expression here, and using the values provided by the exercise, we can calculate everything. The exercise said that the power factor was 0.8 lagging. Therefore the cosine, which is, this is already the cosine of the angle, okay? The angle is the inverse cosine of the power factor, which is 36.87 degrees. This we know, it is 0.02 per unit. This we know, it is 0.05 per unit. Then the voltage regulation is going to be 0.02 times the cosine of 36.87 degrees plus 0.05 times the sine of 36.87 degrees. Okay, calculating this, we reach the voltage regulation as 0.046 per unit. Okay, my friends, this is all the exercise wanted us to calculate, and it was then exercise 3. Let's move on to exercise 4 now. Exercise number 4 now. Find the percentage relation and efficiency for the following transformer. This is a real transformer. We are taking into consideration the losses in the machine. When a load having a lagging power factor of 0.8 is connected to the output terminals of the transformer. Okay, my friends, this is the question. Let's go to the solution. The exercise gave this data. It said that the power system is a 60 Hz one, and that the transformer has these parameters. Okay, we are going to use this data to calculate what the exercise wanted us to calculate. Notice that since the magnetization current, there is going to be a magnetization current here in the magnetization branch. Notice that the magnetization current is much less than the current along the wire. Okay, this current here, I1, represents the current along the wire of the winding of the transformer. And since the magnetization current is much less than this current, we can move the magnetization branch to the left of this impedance here, with only a little impact on accuracy. Okay, the best model uses the magnetization branch here. Okay, but as the magnetization current is much less than this current here, there is going to be only a very small impact on accuracy. We can confidently do this. Okay, and for the rated load of 20 kVA, the load current is, let's calculate firstly the load current, I2 is equal to the power 20 kVA divided by, this is not the phasor, only the magnitude. We are working only with the magnitude. 20 kVA divided by 240 volts. Alright? Therefore, the magnitude of the current is now let's work with the angle. To calculate the angle, we need to use the power factor. The exercise says that the power factor of the load is 0.8 lagging. It means the load is inductive. Okay, inductive loads have lagging power factors. Then the angle is the inverse cosine of the power factor, which is 36.87 degrees. In this way, the load current phasor with a dot here meaning phasor, which is a complex number, is 83.33 phase negative 36.87 degrees amperes. It is a negative. The angle of the current is negative because the load was stated to have a lagging power factor, okay? The primary side current is related to the secondary side current by the turns ratio. To calculate I1 using I2, we need to consider the turns ratio of the transformer. Therefore, I1 is equal to, observe that it is a step-down transformer, meaning that the voltage here is greater than the voltage here. Conversely, the current here has to be less or smaller than. Alright? So I1 is equal to a tenth of I2. Or 8.33 phase negative 36.87 degrees amperes. Subsequently, we calculate the voltages, okay, with the values of the currents I2 and I1, and these parameters here that were given by the exercise. We can calculate the voltages. I'm going to erase here because I'm going to read more space. I'm going to need more space. And V2 is equal to V2 is equal to V load, the voltage here, of the load, plus the voltage drop here caused by I2. R2 plus J X2 times I2. Alright, this is how we calculate V2. And using the values that the exercise gave, okay, we can find that V2, the exercise said that it is delivered 240 to the load, okay? This is going to be our reference. This is going to be our reference, all right? It is 240 phase 0 degrees volts. This is our reference. We are setting as a reference the 0 degrees reference at the voltage delivered to the load. Okay, this is going to be our reference. V2 is going to then be equal to 240 phase 0 degrees volts plus 0.03 R2 plus J 0.07 here is the reactance times the current, 83.33 phase negative 36.87 degrees volts. Now this is the current, amperes. current is measured in amperes. Alright, and calculating, we find V2 equal to 245.52 phase 0.74 degrees volts. Okay, this is V2. And to calculate V1, from V2 we can calculate V1 using merely the turns ratio of the transformer. Okay, this is the high side, this is the low voltage side, then we simply multiply by 10, and V1 is equal to 2455.2 phase 0.74 degrees volts. Okay, this is the voltage V1. Now to calculate the voltage of the source, we use the primary winding impedance, okay? Because this voltage here is going to be this voltage here plus the voltage drop along the impedance of the line. Alright, so Vs is equal to V1 plus R1 plus J X1 times I1. Alright, we're going to use the value of V1 here as we use it here, okay? We're going to calculate as we calculated here. Just see how it was done here, and we're going to use the same here, but observe that R1 is 3 and X1 is 6.5, and using the value of the inductance, the impedance, using the value of the impedance, the voltage, and the current, we find that Vs is equal to 2508.2 phase 1.37 degrees volts. Okay, this is the value of the voltage of the power supply. Subsequently, we compute the losses. The power loss within the transformer can be found as where we lose power. We lose power here in this resistance. We lose power here in this resistance, and we lose power here in this resistance. Then, to calculate the power lost inside of the transformer, we do this power loss is equal to Vs squared over Rc, okay? The voltage here squared divided by the resistance plus R1 times I1 squared plus R2 times I2 squared. Okay, using the values, okay, Rc was said to be 100 kilo ohms. This voltage here we already have. R1 is 3 ohms and R2 is 0.03 ohms. Okay, using the values of the currents we calculated, only the magnitude, alright? You do not need to work with the angle here, only the magnitudes of the currents. We find a power of 479 phase 0.5 watts. No phase. This is real power, not the complex power. The complex power has a phase. This is only the real part of the power, and it is 479.5 watts. Okay, now we can calculate the power delivered to the load. The power delivered to the load is equal to V low times I2 times the cosine of the angle. V low is our reference, 240 phase degrees volts. I2 we calculated, we're gonna use only the magnitude of the current and the cosine of the angle. The cosine of the angle is the power factor 0.8. And using the values, we find 16 kilowatts. Okay? The input power, this is the power delivered to the load, okay? 16 kilowatts, the power delivered to the load. The input power is given by the power that enters the transformer is going to be the output power plus the power lost. And this is going to be 16 kilowatts plus 479.5 watts. And this is approximately equal to 16.5 kilowatts. This is the input power, the power that enters the transformer. With this data, we can calculate the efficiency. Let's calculate the efficiency. We're going to use these values here of power to calculate the efficiency. The percentage efficiency is equal to 1 minus P lost over P in times 100%. Okay, simply using the values, and we find that it is approximately 97%. Okay, this is the efficiency of the transformer. Subsequently, we determine the no-load voltages to calculate the regulation. The no-load voltage, no-load, is the one where I1 is equal to I2 equal to 0 amperes. And in this way, V1 is equal to Vs, which is 2508.2 volts. Okay? And V2 no load is equal to V1 times the turns ratio of the transformer, but inverse, because we are stepping down the voltage. And it is 250.82 volts. Okay? And now we calculate the percentage regulation. The percentage regulation is going to be, this is our last result. It is V2 no load minus V2 full load divided by V2 full load times 100%. simply using these values here, okay, this and this is there, okay, is 250.82 minus 240 divided by 240 times 100%, and this is 4.51%, okay? This is the percentage relation of this transformer, and it is all for exercise 4. Let's continue and go to exercise 5. Exercise number 5 now. A 300 kVA, 2-winding power transformer has iron losses of 2 kilowatts and a copper loss at the nominal output current of 2.5 kilowatts. With this data, find the load level at which the efficiency is at a maximum. Okay, my friends, this is the exercise. The exercise wants us to deal with efficiency and find the load level at which the efficiency is at a maximum. By definition, efficiency is the division between the output power by the total power. But the total power is equal to the output power plus losses. Okay? And these losses are the copper losses and the core losses. Alright? Then we can rewrite this expression as okay? This is the expression of the efficiency. We want to maximize it. We want to maximize the efficiency, and to calculate the load for maximum efficiency, we're going to make use of a variable. We're going to use the variable x here that represents the portion of the output power at full load that produces maximum efficiency. Okay? The core losses are somehow fixed. But the core losses vary with output current. Okay? We do not want the core losses at full load. We want the portion of the copper losses at full load that enables maximum efficiency, okay? And we are going to use this to calculate the maximum efficiency and the output current that enables maximum efficiency. So what we want is to maximize this with respect to output current. The derivative of the efficiency with respect to output current has to be equal to 0, okay? Alright, when the derivative of the efficiency with respect to output current is equal to 0, we have maximized the efficiency. And it is going to be the derivative of this, the derivative with respect to output current of x. We are going to use this variable here, okay, x v2 I2 times the cosine of theta 2 divided by x v2 I2 times the cosine of theta 2 plus the copper losses. The copper losses vary with the square of the output current, okay? The copper losses vary with the square of the output current. Then we write x squared p cu full load plus the core losses. The core losses are somewhat fixed. Okay, and when we take the derivative, we discover that x squared is equal to p core over PCU full load. Okay, where x is equal to the square root of p core over PCU full load. Okay, this is the level of loading. All right, this is the level of loading that enables maximum efficiency. And using the values furnished by the problem, we find that x is equal to 2 kilowatts over 2.5 kilowatts and the square root of it, and we find that it is 0.8944. Okay, and when we apply this to the power rating of the transformer, it was said it is a 300 kVA transformer. Then it is going to be S equal to 0.8944 times 300 kVA, and it is equal to 268.3 kVA. This is the load that if connected to the output terminals of the transformer will enable maximum efficiency. Okay, and we simply multiplied the load factor. Okay, we maximized the efficiency and we discovered that the load level, x that represents the load level for maximum efficiency, we simply used the values that the exercise provided, and we discovered that this is the load factor that enables maximum efficiency. We applied this at the power rating of the transformer, and we discovered the load that if connected will enable maximum efficiency. With this level of load, the transformer is operating at maximum efficiency. Okay, this is all for exercise 5. Let's go to exercise 6. Exercise number 6, a 500 kVA 3-phase power transformer has core losses of 300 watts and full load copper losses of 600 watts. What is the level of load at which the transformer is expected to reach maximum efficiency? Okay, my friends, this is exercise 6, and we're working again with efficiency. And again, efficiency is maximized with respect to output current S. The derivative with respect to output current of the efficiency has to be equal to 0. When we make the derivative of the efficiency with respect to output current equal to 0, we maximize the efficiency of the transformer, and this gives that PCU has to be equal to P core. When the core losses are equal to the copper losses, we have maximized the efficiency of the transformer. Okay? Observe that the core losses are fixed and that the copper losses vary with load level, and it is proportional to the square of the output current. Alright, this here is not this. Okay, the portion of the copper losses that enable maximum efficiency is not the copper losses at full load. This is only a fraction of this, okay? We need to relate this with this to calculate, okay? We know that the copper losses vary with the square of the output current, okay? And we are going to use this P core is going to be equal to the square root of PCU full load, okay? This varies with the square of the output current. X is not the output current. It only represents that while this is fixed, this varies with the square of the output current, okay? But we do not want this full load. We want this. We want to find the portion of the copper losses at full load that enables maximum efficiency, and this portion has to be equal to the core losses. Only when the portion of the copper losses at full load is equal to the core losses, we have maximized the efficiency. Okay? Have you guys fully comprehended what I said? Alright, so X is equal to P core over PCU full load, and the square root of it. And if we use the values 300 watts and 600 watts, we find a load level of 0.707. This is the load factor that represents maximum efficiency, and we simply multiply by the power rating of the transformer, and it is going to be the apparent power of the transformer for maximum efficiency, the level of load that may be connected at the output terminals of the transformer for maximum efficiency is going to be 500 kVA times 0.707, and this is 353.5 kVA. Okay, my friends, this is the level of load that, if connected to the output terminals of the transformer, will enable maximum efficiency of this machine. Alright, my friends, this is all for exercise 6. Let's go to exercise 7 now. Exercise number 7. A 5000 kVA, 230, 13.8 kV, step down, single phase transformer has a per unit resistance of 1% and a per unit reactance of 5%. The open circuit test performed on the low voltage side yielded the following data: VOC 13.8 kV, IOC 15.1 amperes, POC 44.9 kilowatts. With this data, letter A, find the equivalent circuit referred to the low voltage side, and letter B, if the voltage on the secondary side is 13.8 kV and the power supplied is 4000 kilowatts at 0.8 lagging power factor, find the voltage regulation and the efficiency. Okay, my friends, this is the exercise. Let's go to the solution. Letter A wants us to find the equivalent circuit referred to the low voltage side. And to do this, we need to use this data furnished by the exercise. Let's go, letter A. Firstly, we're gonna work on these values here of the open circuit test to find the excitation admittance. The excitation admittance is 1 over RC minus J 1 over XC, which is equal to IOC divided by VOC in the phase negative theta, where theta is equal to the inverse cosine POC over VOC times IOC. Okay? This is how we calculate the excitation admittance. And with the excitation admittance, we can find the, here is XM, okay, XM, not XC, okay, the magnetization components here. Okay, so the components of the magnetization branch are the magnitude of the excitation admittance is the open circuit current divided by the open circuit voltage, which is equal to this value here, 15.1 amps divided by 13.8 kV, and this gives a value of 0.0010942. Okay, this is the magnitude of the excitation admittance. And to find the angle is going to be the inverse cosine of this. POC is 44.9 kilowatts. VOC is 13.8 kV. And IOC 15.1 amps, and we find a value of 77.56 degrees. Okay, and then the excitation admittance is equal to 0.0001092 phase negative 77.56 degrees Siemens. All right, or more if you prefer, which is the inverse of ohm. Converting this polar representation or polar form to Cartesian, we find that RC referred to the secondary side is 4,240 ohms, and the XM referred to the secondary side is 936 ohms. Okay, we already know then the values of the components of the excitation branch. Now let's calculate the values of the series components here. Okay, the equivalent resistance and the equivalent reactance. Observe that the values were given in per unit. To convert this value from per unit to ohms, we need to use a base value. When working, calculating the base impedance at the low voltage side, the secondary, we are working with the low voltage side here. We established that ZB is equal to VB squared divided by SB, okay? We are working here with base values, and we find that for the low voltage side, which is 13.8 kV, the high voltage side is 230 kV. We are working with the low voltage side, and it is 13.8 kV squared divided by the apparent power of the transformer, the power rating 5000 kVA, and this is approximately equal to 38.1 ohms. This is our base impedance, and to convert these values here from per unit to ohms, we multiply by the base impedance here, okay? The equivalent resistance referred to the secondary side is going to be equal to 1% of ZB, which is 0.381, and the equivalent reactance referred to the secondary side is 5% of ZB, which is equal to 1.9 ohms. All right, with these values, we can draw the equivalent circuit. The equivalent circuit is going to therefore be like this. Okay, this is the equivalent resistance referred to the secondary side. This is the equivalent reactance referred to the secondary side, and this is the excitation branch. Referred to the secondary side, and here we have J xm over a squared, and here we have RC over a squared, okay? These values here are already these values here, because here is the primary side referred to the secondary side, here is the value already referred to the secondary side, okay? We have output current here, IS, we have output voltage here, Vs, and here we have input voltage referred to the secondary side, okay? We use the turns ratio to refer from one side to the other, and here the input current referred to the secondary side. Alright, this is the model, and these are the values. RC referred to the secondary side, XM referred to the secondary side, the series equivalent resistance, and the series equivalent reactance, okay? Now let's go to letter B. Alright, this is all for letter A. Let's go to letter B. In letter B, we are requested if the voltage on the secondary side is 13.8 kV and the power supplied is 4000 kilowatts at 0.8 lagging power factor, find the voltage regulation and efficiency. We need to find the voltage regulation and efficiency. Okay, let it be now. The current at the secondary side is, let's calculate the current of the secondary side. This current here is, we know that B out is equal to Vs times Is times the cosine of the angle, okay? And the cosine of the angle was given as 0.8, which is the power factor, okay? The power factor is 0.8. Then to find the current, we simply use the values, okay? 4000 kilowatts divided by the voltage 13.8 kV times the power factor, and this gives a value of 362.3 amperes. This is the magnitude only, and to find the angle we need to consider the power factor. Okay, the power factor was said to be lagging. The angle of the current is negative. The angle is the inverse cosine of the power factor, which is 36.87 degrees. And then the current phasor is going to be 362.3 phase negative 36.87 degrees amperes. Inductive loads cause the angle of the current to be negative. With the value of the current, we can calculate Vp, okay? Vp prime. This is Vp prime. Vp over A is Vp prime. All right, the Vp prime is equal to Vs plus Is times the equivalent reactance referred to the secondary side, the equivalent impedance. Sorry, I said reactance. The equivalent impedance is the equivalent resistance plus the equivalent reactance. And using the values, Vs is 13.8 kV. Okay, Vs is 13.8 kV. It was said that the output voltage of this transformer is 13.8 kV, and we're gonna use the value of the current, this value here, and these values here we calculated in letter A, and when we add this to this, we find that Vp prime, or if I prefer Vp over A, is 14,330 phase 1.9 degrees volts. And to finish we calculate the regulation. The voltage regulation is going to be the percentage regulation. Voltage regulation is going to be Vp prime minus Vs divided by Vs, okay, times 100. And this is equal to, here, this value here, 14,330 minus 13.8 kV divided by 13.8 kV, and this gives a percentage regulation of 3.84%. Okay, my friends, this is exercise 7. Let's go to the last. Let's work on exercise 8. Exercise 8, a 20 kVA, 20 kV, 480 volts, 60 Hertz distribution transformer is tested, and the following data is obtained. This is the data obtained from the open circuit test performed at the secondary side, and this is the data from the short circuit test performed at the primary side. With this data, find the per unit equivalent circuit at 60 Hertz. And letter B, what would happen if such machine is used in a 50 Hertz system? Okay, this is the exercise. Let's solve it. The exercise wants us in letter A to work with the equivalent circuit in per unit. As we are requested to work in per unit, we need to establish base values. Okay, the base impedance of the transformer referred to the primary side is Z base referred to the primary side is Vp squared divided by the apparent power, and this is 20 kV squared divided by 20 kVA, and this is equal to 20 kilo ohms. Okay, this is the base impedance referred to the primary side. Similarly, we're going to calculate the base impedance referred to the secondary side, and this is ZBS is going to be Vs squared divided by S, and this is 480 volts squared divided by 20 kVA, and we find a value of 11.52 ohms. Alright, these are our base impedances referred to the primary and the secondary side of this transformer. Now let's use these values here to find these parameters here of the equivalent circuit. Firstly, we're going to use the open circuit test to calculate the excitation admittance. From the last exercise, we know that the magnitude of the excitation admittance is IOC divided by VOC. Okay, and it is 1.6 amperes, 1.6 amps divided by 480 volts, and this is equal to 0.00333. All right, and the angle is, we already know how to calculate the angle. It is the inverse cosine of P OC divided by VOC IOC, and if we use these values here, POC, VOC and IOC, we find an angle of 66.7 degrees. All right, and the excitation admittance is therefore equal to 0.00333 in the angle negative 66.7 degrees. All right. We know that this is equal to 1 over RC minus J1 over XM. And if we convert this from polar to Cartesian, we may find that RC is equal to, I'm going to put the values here, okay? RC is equal to 757 ohms. XM is equal to 327 ohms, okay? These are the values of the excitation elements, okay? The elements of the excitation branch. We are requested to convert them to per unit. Yes, we need to convert them to per unit, and to convert them to per unit, we just divide by the base. RC PU is going to be RC divided by ZBS, okay, referred to the secondary side, because you see here that it was said that the open circuit test was performed at the secondary side, and if we divide this value here by the base impedance of the secondary side, we find instead of this value here, we find 65.7 per unit, and the same can be done for the excitation admittance, and it is going to be that value that we wrote there divided by ZB referred to the secondary side, and we find a value of 28.4 per unit. 28.4 per unit. Okay, we have already calculated this and this. We are going to calculate now the series impedance. And to calculate the series impedance, we use the short circuit test, which was carried out at the primary side. The short circuit test provides the series impedance referred to the primary side. The magnitude of the series impedance is VSC divided by ISC. We use the values here, 1130 divided by 1 amp, and it is therefore 1130 ohms, and the angle is the inverse cosine of PSC over VSC times ISC. And if we use these values here, okay, there we find that the angle is 76.7 degrees. And in this way, the equivalent impedance is going to be 1130 phase 76.7 degrees ohms. Okay, if we convert this polar form to the Cartesian form, we're going to find that HEC plus J check are equal to 260 ohms plus J, 1100 ohms. All right. All right. And we discovered therefore that HEC is equal to 260 ohms and SHEC is equal to 1100 ohms. But the exercise wanted us to work with the per unit system of measurements and to convert this to per unit. Okay, we simply divide HEC per unit is equal to this value here, HEC divided by the base impedance referred to the primary side, and this gives a value of 0. I'm gonna put it here. These values here are all in per unit. 0.013 per unit, and the same is going to be done to the equivalent reactance in per unit, which is going to be the equivalent reactance divided by the base impedance referred to the primary side. And using the value of the base impedance and dividing, we find that check is equal to 0.055 per unit. All right, this is what the exercise wanted us to do. And now we are going to move on. We are going to move on to letter B. Okay, what did the letter B want? Letter B wanted us to debate whether or not this transformer that was designed to operate in a system whose frequency is 60 Hertz. What could happen if this transformer is employed in a system that uses, letter B, uses 50 Hertz? Okay, to understand what would happen, let's understand that voltage can be written as magnitude times the sine WTV, okay? And flux in a transformer core, is equal to 1 over N, which is the number of turns, 1 over N times the integral of V of T dt. If we integrate this, okay, phi of t equal to 1 over N times the integral of Vm times the sine of Wt dt, we find that the flux is equal to the negative of Vm, the magnitude of the voltage, divided by 2 pi f, which is W, times the number of turns, and this all times the cosine Wt, or if you prefer, 2 pi f t, okay? And if we want to find the magnitude of this wave here, okay, phi max is equal to the magnitude of this. okay, the magnitude of minus Vm 2 pi Fn, which is Vm divided by 2 pi Fn. Okay, and this result here enables us to understand what's going to happen. Okay, see that frequency is in the denominator here. What does it mean? It means that uh, if we increase the frequency, we decrease the flux. Okay, the higher the frequency, the larger. If we increase the frequency, we decrease the flux. This is our conclusion. Okay, so the flux, the maximum flux for 50 hertz is greater than the maximum flux for 60 hertz. Okay, this is our conclusion. The transformer core is gonna need a handle more flux for 60 hertz than for the transformer core is gonna need to handle more flux for 50 hertz than for 60 hertz. What does it mean? It means that if we use a transformer core that was designed for 60 hertz in a system that uses 50 hertz, the core is going to saturate and overheat. Okay? And this is not recommended. The opposite may be done. A transformer designed for 50 hertz can be used in a system that uses 60 hertz. But the opposite must not be used, because a transformer designed for 60 hertz used in a 50 hertz system will saturate and overheat. Okay? This is the conclusion that we get. And my friends, this is the video that I wanted to make. I hope you guys enjoyed it and learned from it. I am a teacher, guys. If you want to book a lesson with me, use my WhatsApp number. Goodbye!